Hey guys, in this video we're going to look at both kinetic molecular theory of gases and effusion and diffusion. By the end of the video you should be able to recall the tenets of the kinetic molecular theory of gases. You should be able to summarize how it affects the pressure, gas temperature, gas laws, and rates of effusion and diffusion. We're going to be looking at the root mean squared velocity, the definition of effusion and diffusion, and then we should be able to describe how the two are the same and how they are different. Lastly, you're going to be looking at Graham's law to calculate molar mass and diffusion and the mean free path.
Our kinetic molecular theory of gases basically just tells us how a gas is going to behave. So if we have an ideal gas, what should the behavior of that gas be? So what's going on the macroscopic scale based on our microscopic components. So first, our kinetic molecular theory of gases states that gases are made of particles with no defined volume, but they do have a defined mass. So gases are made up of particles with no defined volume, but with mass. So they are volumeless in comparison to the volume of the gas itself. So in comparison, with the gas volume itself, so how much volume the gas is occupying, the volume of the particles is insignificant. Okay? So, we would say that the distance between them is so great that we don't even consider the volume that they themselves take up. Our gas particles undergo no intermolecular attractions or repulsions. So when we put them together, they're not going to be attracted to each other. They're not going to repel each other. They're going to essentially leave each other alone, not interact at all. So what this assumption implies is that the particles possess no potential energy. They just have kinetic energy. So their total energy is kinetic in nature. Which is why temperature has such a great effect, or was such an important variable with gases, because that determines what the kinetic energy is, and they are all kinetic energy. Gases themselves are in continuous random motion. So our gas particles are in continuous random motion, colliding and moving, all over the place. They collide, they go a different direction. And those collisions are going to be completely elastic, so there's going to be no net loss or gain of kinetic energy when particles collide. So our collisions are entirely elastic. So no net loss of kinetic energy when gas particles collide. And the average kinetic energy is going to be the same for all gases at a given temperature. average kinetic energy is the same for all gases at a given temperature, regardless of the identity of the gas. So the identity of the gas plays no role in this. And that's kind of the takeaway from this a lot of times, is that it doesn't matter about the gas identity. They're all going to behave the same way. And the kinetic energy is proportional to the absolute temperature, Kelvin. So we're always talking about temperature in Kelvin here. Another reason why we must be in Kelvin is because we relate it back to that absolute temperature. So, our kinetic molecular theory of gases is what kind of brought about our gas laws. So it helps to explain what's happening on the molecular level. So I'm just going to go KMT is our kinetic molecular theory. So it explains what is happening in a gas at the molecular level and at the macroscopic level. Okay. So, um, basically what happens as our pressure and our temperature are changing. So, as gas pressure is increased, the frequency and force of the collisions also increases. And we generally do this by increasing the temperature of the gas. So we can increase our collisions, the force of our collisions, and therefore our gas pressure by increasing our temperature of our gas. So it's all back down to that absolute temperature of the gas, that kinetic energy of your gas, that's going to affect your properties of your gas. Okay, so when we think about our kinetic energy of our gas, we think about the energy that all the gas molecules contain, but we usually think about the average kinetic energy. So our average kinetic energy is based on a distribution of kinetic energies. Across all of the molecules of gas, or of the particles of gas in a sample. Okay, so it's a distribution, right? And we can show this as a graph. basically. So what is going on with our gas molecules? So we can look at the fraction of molecules and their molecular speeds. And we can see that at lower temperatures, we have lower average molecular speeds. At higher temperatures, we're going to increase those speeds. And we also kind of widen that distribution. Okay, and there's a couple of ways to look at our molecular speeds. We can look at either the speed exhibited by the largest number of molecules, which is right there in the center, or the average mean speed of all the molecules. So what is our average mean speed? And then the last, we can look at the speed of a molecule whose kinetic energy is equal to the average kinetic energy of all the molecules. And that is our root mean squared, this one right here. Root mean squared. Okay? So it's going to be slightly different due to differing masses. Right? We are going to have differences in our speed based on our mass, right? So we can have two things that have the same speed, they could have the same kinetic energy, but they're going to have different speeds because they have different molar masses. So this brings us to the idea of molar mass and molecular speed. So just because we say they all have the same average kinetic energy does not mean that they have the same speed. So the root mean square speed is important because the average kinetic energy is equal to 1/2 mass times by our root mean squared value for any collection of gases. So we can use our root mean square speed and actually solve for our kinetic energy. The root mean squared speed can be calculated using the square root of 3RT divided by, let's do a little funky M, where our R is our gas constant, our T is our absolute temperature, and then that is our molar mass. It's uppercase M that I've added some fanciness so it's not confused with molarity. So we can actually see that our molar mass is going to have an effect on our speed itself. So our speed is going to decrease the greater our molar mass is. So since molar mass is in the denominator, the more massive the substance, the lower the root mean squared speed, despite having the same average kinetic energy. So we can see this when we look at our molecules and their molar mass if we have them all at the same average kinetic energy. So if we have them all at the same average kinetic energy, we can see that our molecular speed is going to decrease significantly for our higher molar mass species, and then increase for our lower molar mass species. So anything that's lower in mass, even though it has the same average kinetic energy, is going to have a significantly different molecular speed. And another thing, beyond just just getting from one place to another, that is going to be affected by molecular speed is effusion and diffusion. So the molecular speed of a molecule will affect the rates of effusion and diffusion. And diffusion. So effusion is defined as the escape of gas molecules through a tiny hole into an evacuated space, so a place under vacuum. The escape of gas molecules through a tiny hole into an evacuated space so a space under vacuum, as in there is no other particles present. And then diffusion is going to be the spread of one substance throughout a space or second substance. So here I have an example of diffusion and effusion. So effusion, we've got this pinhole and a evacuated space, and the rate of effusion and the rate of diffusion will be based upon our root mean squared speed. This brings us to Graham's law of effusion, which is going to relate our speed or rate of effusion with our molar mass. So our rate of effusion is equal to square root of the inverse of our molar mass. And we could solve for it using this equation here, where you can look at different rates versus molar masses, and you can see that they have an inverse relationship. Okay, last thing I want to talk about is diffusion and our mean free path. So diffusion is obviously going to be a lot faster if our molecules are less massive. because smaller molecules are going to have a higher rate of speed at the same kinetic energy. Now, with effusion, you're just going from one thing into the other, so you can directly relate it to molar mass, and it's real simple. But with diffusion, we have collisions. So there are collisions that have to be accounted for in diffusion. Like I said, unlike effusion, where we don't have anything, so there are no particles, in diffusion, we already have particles that are there, and because of that, we're going to have molecular collisions. So diffusion will be slower than the molecular speed of a gas because of these collisions. Okay? And anytime that a molecule collides, it's going to go in another direction. That is going to affect what's called the mean free path, the average distance traveled by a molecule between collisions. Because of those collisions, the directions of the molecules are going to continuously change. When they hit, they're going to go into a different direction. We can look at the average distance traveled by a molecule between collisions, and this is called our mean free path. So the average distance traveled between collisions. And that is going to be affected by several things, including the molar mass and the pressure. So if we think about our mean free path, anytime we have a collision, we shift our direction. And if you take and average all of these distances, you can determine your mean free path. So lower pressure is going to result in a lower amount of collisions, and it's going to result in a longer mean free path. So lower pressure, less collisions, longer mean free path, and then of course smaller molar mass, longer mean free path. They can usually kind of escape, get further. Okay, that is everything. I'll see you guys later.